So we're on exponential log equations and inequalities, which means that now we're not just simplifying, but we're actually evaluating and solving. So we're going to be using inverse operations, and hopefully we're all comfortable with our inverse operations. So on part A, when we look at 2x equals 64 and log 3 of x equals log x minus 8, you're kind of like, oh, what do I do? Well, we can use the one-to-one properties. And the reason why we can use one-to-one properties is basically saying if my log base are the same, then I can just solve the argument. So the arguments equal to each other. If my exponential bases are the same, then I can just set the powers equal to each other and solve like I would normally do in an Algebra 2 or Algebra 1 class. So the goal is to transform them so that the bases are the same. And then once the bases are the same, we then are just going to use our regular log functions that we already know. Remember, we're going to use our regular solving equation process that we already know. Does that make sense? All right, so one-to-one property. So when you look right here, we have 2 to the x minus 5 equals 64. Okay, 2 to the x minus 5 equals 64. We can't do anything with yet, and that's because the bases aren't the same. But we want to make the bases the same. So in order to make the bases the same, we're asking, how can I turn 64 into a base of 2? How can I turn 64 into a base of 2? 2 to the what power? 6. Yes, 2 to the 6. So we have, this can become 2 to the 6. Now that the bases are the same, I have 2, I have 2. All I'm going to worry about now is taking the exponents and setting them equal to each other. So essentially all you're solving is x minus 5 equals 6. And can you do that? Yes, I hope so. I really hope we can. It would be terrible if we couldn't, right? So we know that x would equal 11. Does that make sense? Okay, that's what the one-to-one is saying. Make your bases the same, and then you take something from being a pre-cal down to being a pre-algebra. Okay? All right. Here with log, notice that you have a leading coefficient. Your leading coefficients become your power. Okay? Once our leading coefficients become our power, we now are solving x to the 1/2 equals 2 squared. And now this becomes an algebra 2 problem, meaning what is the inverse? Well, how do you cancel out a rational power? Well, the inverse of a rational power is to reciprocate it. So when I reciprocate, that means instead of to the 1/2, it becomes 2 over 1. And what I do to one side, I do to the other. So x simply equals 2 to the 4th, which is did someone say 16? I know it's a tiny space and it's intentionally meant to be a tiny space, but to show you that a lot of these smaller ones can be done mentally, okay? But I'm writing it out so that you can see where the mental steps would come from. Does that make sense? All right. So again, the one-to-one allows us to take something that looks like it's going to be a lot of work and shrink it down. Got it? So for exponentials, they have to have a common base at the same base. And for logs, they have to have the same log of the same base. All right. Are we ready to dive in a little deeper? Ready, set, let's go. All right. So here we have 24 times 1/2 to the x third equals 6. And you're like, I can't do anything with that. Currently, we cannot. So what we're going to do is we're going to manipulate this, right? We're going to use all of our properties and skills to manipulate this into something that we can work with. All right. So the first thing is your exponential needs to be isolated. So I need to get 1/2 to the x to the third by itself. What do I need to do to isolate this? I want this by itself. Who needs to go away? It's being multiplied. So what do I need to do? Divide. So we're going to divide both sides by 24. And we're going to be left with 1/2 x to the third equals 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 over 4. Is that fair to say? 1 over 4 is 1 I need my bases to be the same. So these two, I'm going to convert so that they can have a base of 2. 1/2 becomes 2 to the negative 1. Does that make sense? And it still has x to the third on the outside. 1/4 becomes 2 to the negative 2. So now that my bases are the same, I'm focusing on the powers to solve. So we have negative x over 3 equals negative 2 over 1. How do you solve a fraction equal to a fraction? This goes back to middle school. Cross multiply, we have a proportion. And how do you solve a proportion? We cross multiply and divide. So I'm going to cross multiply. Negative x times 1 is negative x equals 3 times negative 2, which is negative 6. And what am I dividing by? Negative 1. So x equals what? 6. Okay. A lot of times you get stuck not at the pre-cal, you get stuck at going backwards and going back to the pre-algebra or going back to the algebra. You know how to solve proportions. You spent a great amount of time from 5th grade through 7th grade cross multiplying and dividing. I would like to believe at least you were supposed to. Okay. All right, let's try to log. Again, the goal is to make sure the logs are the same and they are isolated. Well, our power rule allows us to do what with our coefficient? Turn it into a power. So now we're working with log base 3 of x squared equals log base 4 to the third. Once your logs are the same, all that matter are the arguments. X squared equals 4 to the third. So we have x squared equals 4 to the third. A lot of times we want to go and take the square root, but with when we're dealing with exponents, if you just use the reciprocal rule and work with the rational, it works a little bit better and it helps you manipulate a little faster. Does that make sense? So the inverse of 2 would be 1/2. And what I do to one side, I'm going to do to the other. So we're left with x equals 4 to the 3/2. And now I can simplify this. So x equals, I'm taking the square root of 4 and then I'm cubing it. Because remember, a rational power means your numerator is your power, your denominator is your index. This goes back to Algebra 2. How do you manipulate this? So your numerator is your power, your denominator is your radical index. So we're taking the square root of 4 and then we're going to put it to the third power. What is the square root of 4? And 2 to the third. So my final answer would be 8. It's a puzzle of all little things that you already know. How are you feeling? Okay. Again, you have to go through the motions. You have to apply the math. All right. So on this one, we have log base 2 of 4x equals 5. In this case, we do not have another log on the other side. When there isn't a log on the other side or an exponential on the other side, what you're going to do is use this actual inverse. And the actual inverse of log is what? An exponential of the same base, right? So if I have a log only on one side, then that's when I'm going to use the exponential rule, the inverse of it, okay? So notice here, there's a log, a singular log. I shorthand this and say I'm just going to raise it to the base, right? So whatever my base is, I'm raising both sides to that base. My base is 2, so I'm raising both and turning both of my sides now into powers. What that allows me to do now is this cancels out the log because the base of your exponential and the base of your log are the same. And that leaves me with 4x equals 2 to the 5th power. What is the last step I need to do to get x by itself? Divide by 4. And what I do to one side, I have to do to the other. So we get x equals 2 to the 5th is 32 divided by 4. And 32 divided by 4 is, everybody, somebody? 8. We need to know our basic 10 by 10s, guys, for the non-calculator part. We need to have a little around the world practice to get our multiplication skills up. Bringing back that 4th and 5th grade. Okay. Now, the difference between example 4 and example 5 is that example 4 only had one log, right? On example 5, I have 2 logs, which means that I have to use my log properties to condense. Okay. So here we're going to have to condense. Which log property am I using to condense? I'm going to use product. And the reason why I'm using product is because we are adding. Product says that when I'm adding 2 logs together, I can make them 1 log by multiplying their arguments. Do you remember that? So this is going to become 1 log, and the arguments are going to be x times x plus 15 equals 2. So we've now condensed. Once I've condensed down to 1 log, I now can use my inverse. Okay? When there is not a base, what is my base? 10. This is common log. And so when there is no base, that means that the base is 10. So I'm raising both sides to the 10. The purpose of here is to cancel out the log. And we're going to be left with x times x plus 15 equals 10 squared. This now takes it from being a pre-cal to being an algebra 2 problem. So now we're back to algebra 2. Algebra 2, looking at this is the setup for a quadratic. Hopefully we all see that. Because we would distribute and need to make one side equal to 0. Okay, so I'm going to distribute my x, and I'm going to get x squared plus 15x equals 100. So I'm left with x squared plus 15x minus 100 equals 0. Remember, this is a simple factor. So I'm asking myself what multiplies to give me negative 100, but will add to give me a positive 15x. So what 2 numbers multiply to give me negative 100, but will add to give me 15x? What kind of 5 and 20? There we go. A negative 5 and a positive 20. Negative 5 plus 20 is 15. Negative 5 times 20 is negative 100. So therefore, my solutions would be x equals what? X equals 5 and x equals negative 20. Okay? One of these is what we call an extraneous solution. And it's called an extraneous solution because it'll produce a negative log. A negative argument. And you cannot have a negative argument in the original. So when I look at this word right here, it says avoid extraneous solutions, right? By avoiding extraneous solutions, you're going to take your original values and you're going to substitute them back into your values and substitute them back into the original equation. If it makes my argument negative, it is an extraneous solution and not a real solution. Does that make sense? So if I plug 5 into both of these, this is going to stay positive, correct? So 5 is a real solution. We're good. However, if I plug negative 20 in, it's going to make both of my arguments what? It makes both of my arguments negative. So this is what we call an extraneous solution. Okay. So unless it asks for the extraneous, you're only going to provide the real. And our real solution is x equals 5. Okay. Because again, your arguments have to be positive for log. And that goes back to being the fact that an exponential does not have a negative output, right? Okay. How do we feel? Fine. It's different. I like this part because you're actually getting a solution. And so for me, it's like satisfying because I have an end game. All right. Next, here we have 8 to the x minus 3 equals 26. And you're like, the bases are completely the same, completely different, and there's no possible way for me to make them the same. Oh no, what do I do? You give up, you cry in the corner, and you run away? No, you use log. You're going to use log, okay? When this happens, you have to use log. We don't give up and cry in a corner. We use the log of the base, okay? So we have 8, which means that we're going to use log base 8. So this becomes log base 8 of 8x minus 3 equals log base 8 of 26. By taking the log of that base, it's going to set our variable free. So our variable is now free. X minus 3 equals log base 8 of 26. What's the last thing you need to do to get x by itself? Add 3. If this is on a non-calculator, this is where you stop. This is your exact answer. Log base 8 of 26 plus 3. If it's on a calculator part, then you plug in and get an approximate value. Does that make sense? And this is your exact. Okay. And then I would, if I needed the approximate, I would plug it into the calculator and round to the nearest 3 decimal places. All right. So again, if it's impossible for our bases to be the same, we're going to have to use our log properties. Okay. So again, on this one, we have base E. So we're going to use natural log, right? When I have base E, that means I'm going to use the natural log. So we're going to take the natural log of e to the x equals natural log of pi to the 1 plus x. On this side, what this is going to do is going to eliminate. So we come down to x equals the natural log of pi 1 plus x. Okay. Our power property allows us to do what with this? Make it a coefficient. Our power property says that your power of your argument for a log can become its coefficient. So we get x equals 1 plus x natural log of pi. This, you cannot just move x. Well, you have to move all of it. You have to move 1 plus x together, and you have to divide and all that stuff. So before you do anything, you're going to get rid of parentheses so that you can move terms with the same variable to one side, which means that we have to distribute the natural log of pi. So we get x equals natural log of pi plus x times the natural log of pi. Remember, natural log of pi is just a number. It is nothing super spectacular. It's just a very weird number that goes on forever. So now I can move this term because it's now separated from this term, which means I'm going to subtract. And what I do to one side, I do to the other. And when I subtract, I can now factor out my x. So I'm left factoring out the x. I'm left with 1 minus natural log of pi, if I can write. Equals natural log of pi. And now you can isolate your x by dividing by this entire thing. So x is exactly natural log of pi divided by 1 minus natural log of pi. And that is your exact answer. It again is a world of manipulation. Okay, so this is all when you don't have a calculator. The last piece of these notes is if you are given a calculator, what you can do. I'm going to model it with the TI-84, and then I'm also going to model it with Desmos, because more than likely most of you will have used Desmos, but you will also have the 84 at your hand as well. So I'm going to show both, and then you can decide which one you prefer. All right. So with the TI-84, this is what it looks like. When you're solving, you're simply just putting in your Y1 and your Y2. So your Y1 is going to be your left side. Your Y2 is going to be your right side. And the goal is just to adjust your window in order to find their point of intersection. Okay. You can do it that way. You also can go do it by table. By table, you would need to change what it's counting by. And that seemed to me is just more annoying, but you can do it also by table. Okay. So that would be with the TI-84 or any TI device would be finding the intersection, adjusting your window. Okay. On your lovely handheld calculator, so I'm going to go to our home page. I'm going to open up my Desmos. On here, if you're solving, you're going to simply, again, just put in the two equations. So we have y equals 2, not capitalized, y equals 2, shift. I like to put it in parentheses to guarantee that it doesn't shuffle, because sometimes it does weird things. And it says equal to 9. So I'm looking for when does y equal 9? I would adjust my window so that I can see it, which just means pulling it down. And I would come over here and click it. And then you can save it. And there's your answer. Okay. There's really nothing else to tell you. If you mess this up, you mess it up. I don't know how to save you. Okay. So hopefully don't mess it up. No one should ever miss a problem that's solving an equation on a calculator part of the test, should we? We should not. Okay. But you do need to make sure that you have isolated your exponential. So notice that my exponential is by itself. And then I proceeded to find that point of intersection from there. Got it? All right. That concludes that part of the note.